Hi, this is Raphael bringing you the third tutorial on how to use HAL, the hybrid agent-based library. And in this tutorial, we're basically going to be talking about some sort of miscellaneous features that I didn't mention in the previous tutorial because they are sort of not necessarily needed to construct this like minimal model, but they're useful stuff and sort of fundamental. So I think it's good to go over this stuff sooner than later. So to start with, I want to talk about a few IntelliJ features that I use all the time. So we already went into one of them with using Alt-Enter or Option-Enter to look up any potential solutions to errors that you see. And that can be very, very helpful. Another one is these sort of autocomplete statements. So as an example, I don't really ever type for loops out in like the old-fashioned way. So like, like whatever, right? It takes forever. What you can do instead is just do for I and then tab or enter, and it will automatically sort of generate the, standard for loop syntax. And you can, name the iterator whatever you want. And you can, set the iteration limit. And you can always go in and fix this stuff up later. So I use tab to sort of jump from one thing to the next and as I'm completing this for loop design. So that's kind of helpful. And another example is when you're iterating over a grid using this, where is it? In the step cells function. We have like for every cell in this. To generate that quickly, you can just type ITER and then enter a tab. And we can give it this, and it'll know, okay, we want to iterate over the cells, and so on. Right, so once again, just using tab to jump between the fields, and then I can enter the body of the for loop. So, because you write for loops all the time in Java, it's a useful to have a little trick to speed that up. Another one that you see all the time is public static void main. Right, this whole thing you have to enter it every time you put in the main function, which you need to run a program. So they put another shortcut for that, PSVM, and that'll fill in your main sort of statement for you. So that set is pretty useful. Another thing I do use often is refactoring. So like if I want to rename something, like say I wanted to change, so like this color variable, for example. So this color variable shows up 3 times. If I wanted to change it to like capital C color, I change it here once, but then I have to change it 2 more times, and that's sort of a pain. So what you can do instead is you can right-click on the variable or do Shift F6, but you go to Refactor, Rename, and then you can change the name in one place, and it will search the code for you and change all of the other names that relate to that variable to the proper name. And it'll do this smartly. It won't just look for anything that says color and change it. It'll find that variable where it's mentioned again and change it just there. So that's pretty helpful. And then another one that I use all the time is find usages. So if I want to know where a function is being called, like say I don't know where step cell happens, I can right-click on it and click Find Usages, and then it'll show me, using the sort of file tree, all of the places in other files as well where this function is mentioned. So it can be very useful for seeing how your program interconnects with itself. And then another sort of related feature is I can do go to definition. So I can right-click on this and go to, or declaration. And that will jump me back to So another useful feature that I use all the time as well. So another useful feature that I use all the time as well is finding the usages of a variable. So I can, for example, see where this get agent function is used by clicking here, Find Usages. So right-click and then clicking there. And you can see it'll show you in all of the files in your entire project where that function is being used. So if you end up with a pretty complex program and you're trying to track down when do I call this function because maybe it's producing an error or something, you want to see all the times that happens, you can use that to find that. Another related thing I do all the time is going to the definition of a function. If I forget how the function works or whatever, I can go to the declaration and then I can see, okay, this is the body of the function, so this is all it does, just gets me the agent on the grid. So that's pretty useful stuff. So from here, we're going to go into ways to change this model to make it a bit more colorful, as well as basically looking at how we can assign properties to our agents, because that's somewhat tricky in HAL, and so I wanted to go over that. So to start off with, say we want each of these cells to have its own special color. So we can define a variable in the cell that's its color. And then we can create an initialization function where we set up this color. And here we're going to use the util.rgb function. So we can pick a random doubles, and that will give us our RGB components. I'm just going to copy and paste this. So now, whenever we call this function, the color of the cell will be set to a random color. And then all we have to do now is call this function at the appropriate time. And basically, whenever we create a new agent, if it's going to store any internal variables, we have to make sure we set those variables when the agent is created. So basically, whenever you call this new agent function, you have to, or you should, do some initialization as well. So the new agent function returns the agent, so we can call the init function directly on the return of that function. So now, when this evaluates, it will return an example cell, and then on that example cell, we're calling init. And now each cell will get its own color. So to make that stand out, we have to make sure that we draw using the color of the agent. So if this agent is not equal to null, we should assign it now to a variable. So example cell equals getAgent. And then we can say if cell is not null, then the color should be equal to the cell's color. Now each cell should have its own color when it's first generated. So here as well, we should call the init function again to make sure that the first cell also gets a color. And another thing that I was sort of annoyed by last time around is that sometimes the first cell just sort of dies off without anything happening. So what we can do instead of just creating a cell once and hoping that it survives is we can check if the population drops to 0, and then if that's the case, create a new cell. So we'll just do that inside this for loop. So every time step, we're going to check if all the cells have died, and if so, we'll make a new cell. So we need the model get population. So the model always stores the population of the full set of agents. So if everyone's dead, we'll create our agent. That way, we'll always get a new cell if our population drops to 0. So now if we run this, it should be a bit more colorful and also a bit more reliable. So that's fun. And then, right, so the last thing I wanted to talk about is the division neighborhood. To go into a bit more detail on how neighborhoods work with HAL, because it's somewhat complicated. And I think it's worth sort of pulling the hood back, or pulling the hood open, if you will, and checking out how it works under the hood. So we can use the debugger to sort of examine the code more carefully as it's being executed, and that should help enlighten us a little bit on how the neighborhoods work. So to use the debugger, you can say I added a breakpoint just by clicking on this sidebar. Breakpoints allow you to stop execution of the program at a particular line once the code reaches that line. So you can see I put this breakpoint on this line 24, which is where the neighborhood is first being used. So now we'll be able to see the neighborhood in action. And to run it, you click this little bug button, or a debug button, I suppose. So you can see now we've stopped. This little blue highlight shows that we're currently paused at this line. And one nice thing is you can see the complete stack of functions that were called to get to this point. So I can click on these and go back and see how I got to that spot. So we start off in main, we got to this line, and then we went to the step cells function, in which we called step cell for one of the cells. And then inside step cell, we got to here. So this is kind of neat, especially if you have multiple calls to a function that happen in different parts of your code. And then here we can look at all the variables that exist at this, when this function is called. So these are all the variables that are associated with the agent. So my grid is what gets returned when you call the G function. So we can look inside there to find the division neighborhood. So you can see we open that up, and here's the division neighborhood. So down here, from entries 4 to 11, we have the set of indices that define the von Neumann neighborhood. So sort of what I was describing earlier. We have 1, 0, -1, 0, 0, 1, 0, -1. And then you can see up above, we have 4 zeros that just sort of start before the set of coordinates. So what are these for? These are used to store the valid positions that map hood or map empty hood finds. And that's what's used later on. So we sample the neighborhood by picking randomly from the number of options that we found, picking one of the indices from the division neighborhood up to that number of options. So if we find 4 locations, we're going to randomly pick from the 4 starting values in here. And that's how we know which index to divide to. So just to make this a bit more clear, and to show you how the debugger works in a bit more detail, I'll show you this stepping functionality. So if you want to look inside of a line and see all the functions that get called, you can use this button. If you want to skip over that line, you can use this to sort of go to the next line below without going into any functions that are called on that line. And then this allows you to just exit the function that you're currently on altogether. So first we'll do step in, and you can see we're calling get my grid. So that's just the first thing that has to happen. In order to get the neighborhood, we have to first get the grid. And now we're actually going to do the map empty hood function. And it's just going to run through some stuff, blah, 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 blah. Okay, so here's the actual guts of the map neighborhood function. And so we're going to just step through that and see what happens. So you can see here that it's actually, there's some logic that happens, but it set the first index of the neighborhood to some value. And that is the position of the cell, or sorry, a position around the cell that it can divide into. We go again, do this loop. We set another position, so this is the second index. So the first one was what 1, 0 maps to. The second one was what -1, 0 maps to, and so on. And then at the same time, we're also counting the number of valid points. So at the end, we're going to return that number of valid points. And that's what we set options to in our program. So here options is 4. And so long as we have options, we'll divide into one of those positions. And that's how this whole thing works together. Now, if one of these coordinates didn't map to an empty position, then we would be leaving out one of these values. So 3 would be left as a 0, and the 3 valid coordinates would start from 0 to 2. They'd be stored here. So we'll skip over coordinates that aren't valid, essentially. And so I'll just show you step out real quick. That says, like, okay, I'm done with step cell. I want to go to the function that called it. Then we're back to step cells. I can step out again. Now I'm back at main, and so on. And then if you're sort of done with the debugger, you can always turn off the breakpoint and click this little play button, and that will resume the execution of the program. Or if you want to stop again somewhere, you can put a breakpoint somewhere else or leave it, and then hit play again, and that'll resume. So if I just run this normally, then we'll get the usual visualization and everything. So hopefully this was helpful. Next time we'll do off-lattice model. So we'll see you guys then.